plan for today is to continue discussing learning theory, and we will study the behavior of the estimation error. So, as we discussed last time, the empirical risk minimizer provides you a classifier Fn star. This has a true risk of Fn star. And we already predefined the function class F. The best possible risk on this function class F is R star F. And our goal was to upper bound this difference between the two risks, and that's what we call estimation error. Oops. And we had this theorem that this is less than 2 times the supremum over your function class F. The empirical risk of a function minus the true risk of that function.
Is this the notation? This R star F?
This R star F, that's the same as we had before. The best risk on function class F. That's what we used. Okay? So that's the best risk on function class F. That's the best true risk on function class F. That's the true risk of the function your algorithm provides after seeing n data points. This is the estimation error. And we have this theorem that this estimation error can be upper bounded 2 times the supremum of this difference. So what's this? For any function f, this is the empirical risk of that function, and this is the true risk of that function. And then we were going to bound this difference. And to bound this difference, we used Höfding's inequality and proved that if your function class has capital N elements, then this supremum can be upper bounded this way. This supremum is a random variable, so the bounding, we bounded this random variable using tail inequalities. So the probability that this random variable is bigger than epsilon, we proved that that's smaller than a number. And when we used inversion, then we got this inequality. The issue is that those function classes that have finite elements, they are not that exciting. And then we started to think about what to do in those cases when it has infinite number of elements. And to analyze this behavior when the function class has infinite elements, we started with this observation that this R hat and F cannot have arbitrarily many different behaviors. If we are thinking on classification using the 0-1 loss, if you have n training points, then this could have only 2 to the n different behaviors, because this guy can only be 0 or 1. Oops. All right. So our goal will be to bound this random variable, and the key step will be that we proved that this random variable in some sense is close to its expectation. We used the McDermid inequality to prove that. And then we just needed to upper bound it, the mean, the expected value of this random variable. Right, so this is the McDermott inequality, which says that this random variable we care about is close to its mean. It's close to its expected value. Right, so this was the picture. We have n random variables. As we increase n, the random variable is getting closer and closer to its mean. And so it's enough to upper bound, after McDermott's inequality, enough to upper bound the expected values. All right, then we introduce the notation of shattering coefficients for a function class f. And we mentioned that this expected value can be upper bounded with this so-called VC inequality, where this guy here, S of f, n is the shattering coefficient. And if you put everything together, so with McDermott we proved that this supremum is close to the expected value. This expected value can be upper bounded with this. If you put these things together, then you can prove this inequality. Right? And then we started to analyze these shattering coefficients. Any questions so far? So we all did this last time, right? So we introduced the notation of S of f x1 xn which was just this expression, the maximum different behavior of this n-dimensional vector, that you have n training points. For each of them, you apply f function f, and you count how many different n-dimensional vectors you can get in your function class f. And that was sf x1 xn. And the shattering coefficients, the n shattering coefficients sfn was defined as the maximum of this sf x1 xn over all x1 x2 xn. Right, and then we define the VC dimension as the first sample size where this sfn stops behaving like 2 to the n. Right, so we looked at some examples like linear classifiers where, for example, in 2D, when n was 1, n was 2, or n was 3, then this sfn was 2, 4, and 8. But after that, SF4 was less than 16. And then we said that the VC dimension in this case was 3.
So it's the last dimension.
Last sample size where it's still 2 to the n. Right? And that was the notation. If the VC dimension is n, then you can find n points in your domain such that those n points can be shattered. That is, no matter how you label those n points, what the class label of those n points are, there will be a classifier that can solve perfectly that classification problem. But if you have n plus 1 points, then it doesn't matter how you choose those points in your domain. Your opponent could always choose a labeling such that you wouldn't be able to classify those points. Any questions so far? So the VC dimension in some sense measures how rich your function class is, how complicated functions you can allow. Because if you have, say, n points, and the VC dimension is, say, 2 to the n, the maximum. Sorry, not the VC dimension, this shattering coefficient is 2 to the n. It means that for any kind of labelings, you can find a classifier that would be able to solve that problem without error. So you can fit very complicated functions to those points. So in some sense, it means that you have to be careful to keep this VC dimension small, otherwise you might be able to overfit.
What
what makes us to think that it is not going to overfit if it is less than 2 to the power of n? Maybe it's
So,
still large.
It could be still large, I agree. I'm just saying if it's 2 to the n, it means that you cannot really learn anything, right? Because for any labeling, there would be a function that would perfectly fit your training set. And it wouldn't mean anything how to generalize for larger sets, right? But you are right, it could be still large. But the issue is that if you, so we see that if you keep this VC dimension, so it's a fixed number, then after this curve here, it stops behaving exponential. It will be polynomial with the degree VC dimension.
So you want your sample size to be much bigger than the VC dimension?
Yes, yes, sure.
And this is universal no matter what f is?
It's, so f has to be in your function set, but it's universal in that sense that it doesn't matter what's your distribution pxy is. All right, and then I think this is where we stopped last time. So let's see some examples. So one example can be that let the domain be two-dimensional. And let's just use, instead of linear classifiers, let's just use decision stumps, which means that your decision lines could be either vertical or horizontal only. Okay? So that's your function class, either vertical or horizontal lines, straight lines. And then the question is, what's the VC dimension of this function class when the dimension of your domain is 2? Okay, so let's think about this. So if we can see that there's a placement of 3 points that can be shattered, then it means that the VC dimension is at least 3. So if I, for example, if I can prove that these 3 points can be shattered, that is, I can see all the 8 different behaviors on these 3 points, it means that the VC dimension is at least 3. Right? And we can see that it's indeed the case. So if we have these 3 points, it doesn't matter how I label them. There are 8 different labelings, right? It doesn't matter which one I choose out of these 8 different labelings. There would be a classifier, either vertical line or horizontal line, that would be able to perfectly classify these points. Any questions so far?
So it has the same VC dimensions as the linear separator?
The VC dimension is just a number.
Yeah, even though it's a much smaller class.
Right,
it's a subclass of
linear classifiers, right? Yep, but still.
It's still the same VC dimension.
Okay, so let's see what happens when we have 4 points. So that's clear so far. We can see the VC dimension is at least 3. If I can choose 4 points, such that on those 4 points I could also see the 2 to the 4, 16 different behaviors, that would mean that the VC dimension is at least 4, right? So let's see if we can find those 4 points. So for example, what happens if these 4 points look like this? Then I can see that if I choose the labeling like this, then I wouldn't be able to classify these points with decision stumps. Yes?
Wouldn't that imply what he said, that because these are subclass of the linear classifiers and it already attained 3, at least is 3? Then
Let's assume we don't know the VC dimension of linear classifiers. Okay, I just want to see examples. Yeah. But you are right. All right, so I can choose this labeling that I wouldn't be able to classify perfectly. What happens if the 4 points look like this? Can I find a labeling that I wouldn't be able to classify these points?
yeah.
Yes.
The center one is plus and all the others fine.
Exactly. right? And another case could be if the 4 points look like this, then yes, as I can see that if I choose this labeling, again, I wouldn't be able to classify them with decision stance.
How do you prove that?
So the proving, yeah, that's the art part or the tricky part. So you have to be careful, and sometimes it's tedious. But I hope that you can see that with some effort we would be able to prove this, right? It's just geometry in this case. But you are right that there's no general recipe how to prove this for arbitrary function classes. That's the art part. Okay, but now we can see that because of that, the VC dimension is 3. Okay, let's see another set of classifiers. So in this case, so any question about this? Sorry. Is it clear that the VC dimension of decision sums is 3 in this case when the domain of is the dimension of the domain of your features is 2? Okay, so then let's see another class. So in this case, the classifiers look like axis parallel rectangles. So the classifier can say that inside of my rectangle, it's class 1. Outside of this rectangle is class 0, or class minus, class plus. The domain of the features, again, is a 2-dimensional Euclidean space. And let's calculate the VC dimension of this function class. Is the goal clear? So this is my function class. We want to see the VC dimension. Again, we choose 3 different points. If we can prove that for any labelings of these 3 different points, the classifier can always perfectly classify these labelings, then it means that the VC dimension is at least 3. And indeed, no matter how you choose the labelings, you can always fit a rectangle that's compatible with your labelings. Okay, so the VC dimension, can you see that? The VC dimension is at least 3. So what happens if we have 4 points? So for example, these 4 points. Now there are 16 different labelings. But even for that 16 different labelings, we can prove that our classifier could perfectly classify those points no matter what the labelings are. Okay, so I try to list some of the possible labelings. So for example, if the labeling looks like this, you just fit a classifier like this. If your labeling looks like this, you fit a rectangle like this. If your labeling looks like this, you fit a rectangle like this, and so on.
Can you do the opposite? I mean, everything that's inside is positive, or positive? Can you do either way?
Sure. So I just choose the classifiers. So that was my function class. That inside.
So inside it has to be.
Yes. So that's how you fix your classifier. You say that inside of this rectangle, it has to be this class. Yes.
Then only the case of negative plus negative in a line.
So you choose your 4 points. And then your opponent chooses the labelings, right?
If you can only classify negative points inside the rectangle, then negative plus negative cannot be classified in the.
So can you draw that example? We have 4 points now, right? Or you just check? Okay, so I'm the one who can choose the points first, and then my opponent chooses the labeling. I decided to choose my 4 points in a general location. Okay, so I choose these 4 points. Now you are my opponent. You choose the labeling. So what labelings you would choose for these 4 points? So you cannot choose these 4 points because I choose the points. That's the game. I choose the points, you choose the labelings. Okay, so my point is no matter what labelings you would choose, I could fit a rectangle to those labelings. That would solve the problem. Okay, so that's the game. Any question? Does it make sense this way? So I choose the points such a way that on those points I chose, I want to show that it can achieve 2 to the n different, I can see the 2 to the n different behaviors. In other words, no matter what labelings my opponent, say you, choose, I should be able to classify them. But I make the first step. I choose the points in the domain. All right, so let's see what happens if we have 5 points. So now we know that the VC dimension is at least 4, right? What happens if we have 5 points? Then we can have these different cases. For example, 4 points are collinear. I choose these 5 points this way. Then it turns out, if I choose these 5 points this way, my opponent can choose labeling such a way that I wouldn't be able to fit a rectangle that's compatible with that labelings. Okay. If I choose the 5 points this way, again, you could choose a labeling that's not compatible. You could choose a labeling that I couldn't classify with my function class. If I choose these 5 points, again, my opponent could choose a labeling that I cannot fit a classifier there. Yes?
Can we not invert the classifier? Because if we do
So we've already so the setup is that you fixed the function class, and the function class was that inside the rectangle, that's class 1. All right, if we have these 5 points, any comments, Alex?
No, I was just mentioning that as you increase the number of points, basically, at some point you will run out of possibilities. And so now what we're seeing already is that the complexity is dependent on the layout of points. So in other words, we're seeing that there's a gap opening up between what you can do depending on the distribution of the data. And that's actually going to be kind of a big source of discrepancy between worst case bounds and what happens in reality. That in reality, data is much more nicely distributed than what the worst case bounds give.
Sure. Right. So we discussed worst case scenario here.
And this is why often learning theory bounds can be rather loose, because it's just much harder to prove something for the typical case.
Yeah, so word is not always that cruel than the theory shows, right? Okay, so if we have these 5 points, again, my opponent can choose a labeling such that I wouldn't be able to fit a rectangle to those points. So bottom line, no matter how I choose those 5 points, my opponent could choose a labeling such that with this predefined function class, I wouldn't be able to classify those points perfectly. So in this case, the VC dimension, because of that, it's 4. Any questions?
Do you have any measure on so for example, the pathological examples in the worst case scenario, do you have a measure of how often do that happen? Like for example, in optimization, I know that sometimes your worst case scenario just happens on a set of measures 0. So you know that almost surely your algorithm is
right. So I think it depends on your distribution of your input outputs, right?
But for example, in R2, right? Like linear points have dimension, measure 0.
Right, but still you have to start with the assumption on distribution of x and y's for that, right?
The definition of the VC dimension doesn't depend on the distribution.
Right, so that's why it's a worst case plan. So it's a universal bound.
So then my question is, do you have a VC dimension definition that depends on the distribution that makes the bounds tight.
So right, so there are better results than this. So let me just say this. Okay, there are even data dependent bounds as well. So in some sense, these bounds are just depending on the sample size. There are bounds that depend on the data as well. So there are much better results than this. Okay, so so let's come back to our theorem that we proved here. So we had this theorem that the expected value of this supremum we care about, that could be upper bounded with 2 times square root logarithm, 2 times shuttering coefficients divided by n, and square root of the whole thing. And another corollary was that the probability of that this supremum is bigger than t could have been upper bounded with this expression. Again, this expression is depending on the shuttering coefficients. And what we are going to do now is that we will upper bound these shuttering coefficients with the VC dimension. Okay, so this theorem says that the probability sup f is in function class f, the empirical risk of f minus the true risk of f. This is a random variable, so the probability that this random variable is bigger than t is smaller than 4 times squared shuttering coefficients times an exponentially decaying term. All right, so there is an important lemma which is called Sauer's lemma, which says that this shuttering coefficient can be upper bounded in this form. SFN is not bigger than k is going from 0 to the VC dimension of the function class f, and n choose k. And of course we already know that SFN is less than 2 to the n. So, you know, a very, very, very naive theorem could be that I just replace this SFN with 2 to the n. But that's a very loose bound. We want to upper bound this SFN because this is exponential n. We want to upper bound this SFN in terms of VC dimension. And if you look at this guy here, what's the nice property of this?
Polynomial.
Right, it's polynomial in n. So far we had an exponential bound on SFN. But if you know the VC dimension, then it turns out that this SFN can be upper bounded using this polynomial form. So it's a polynomial that can be, you know, much tighter than exponential. And two very simple corollary is that from the Sauer lemma, you can prove these two inequalities, that SFN is less than n plus 1 to the VC dimension. It's very cute, right? So it just says that this guy is less than this polynomial with VC, where the order of the polynomial is VC dimension. Or another form sometimes we use is this. Again, it's a polynomial with degree VC dimension. And you can see that if, say, the VC dimension is bigger than E, say at least 3, then this could be much tighter than this. Okay, here is a quick question. Can you prove this in a minute from that? So I'm just wondering if you can see how this follows from that.
You just prove it from induction.
Induction, that could be,
Binomially.
yeah, it's just think about what this using the binomial theorem. Anyhow, it would be nice if you could spend a few minutes at home and prove these inequalities.
Is E like the 2 point? Like
Yeah, that's E is the Euler constant. That's why I'm saying the VC dimension is bigger than say 3. Then this term just looks better than this.
Those are asymptotically the same, right? That goes to infinity.
Sure, but these are finite results. Any question about this? So can you appreciate the beauty of this? That now I could just put this n plus 1 to the VC dimension here. And then I would have an inequality that bounds this expression. And we already know that this expression bounds the estimation error. So we do have a bound on the estimation error in terms of VC dimension. And quite often, you can calculate the VC dimension for certain function crosses, or at least you can bound them. For example, for d-dimensional linear classifiers, we already know that this VC dimension is d plus 1. So I could just put d plus 1 here and plug these guys here.
It used to be hard in general to bound it from above, from below.
Very true. Generally, it can be hard. But for certain important special cases, we know how to bound this.
So the smaller the VC dimension, the better our generalization.
Yes. If the, say, VC dimension is infinite, these are meaningless, these theorems.
Yeah, but on the other hand, the farther away your R F star F is from the true.
So can you repeat your question?
I'm saying the smaller the VC dimension is, the farther your true risk is from your true risk on the best function you have.
So let's go back.
Yeah, the approximation error.
Oh, sure. Right. So there are two things. We care about the estimation error and the approximation error as well. Here we assume that you fixed your function class f. And then we studied how the estimation error behaves. And you are right, what in practice people do, that you actually increase the function class as well as you have larger and larger training points. You increase the complexity of the function class, and you can even measure that complexity with VC dimension. And you do that because you want to minimize the approximation error as well. So if your VC dimension is very small, then you would always have a big approximation error here. You want to avoid that too, because ideally you want to have classifiers that in the limit would achieve the base risk. Good? Okay, so back to Sauer's lemma. If we have time, we can prove this Sauer lemma maybe in 10 minutes. Or might be 15. Let's just skip that proof for a sec, and let's see the corollaries of this lemma, and just accept that we prove this. Okay? So the statement of that lemma is clear for now, right? All right. So say we prove the Sauer lemma, and so from now on we know that SF n is smaller than n plus 1 to the VC dimension, and we also know that this is not bigger than n times e divided with the VC dimension and putting this to the VC dimension. Okay, so let's accept that we know this. And let's see the corollaries of this. So we already proved that if the function class f has n elements, then the expectation of this supremum we care about could be upper bounded with log 2 times n divided by 2n.
This BC inequality, isn't it straight from the upper inequality?
This one?
Yeah, because you know that SFN is the most, like effectively that's the number of different functions you have. That's like the n of the. But if you replace big N by SFN.
So why can you do that?
Because you know that even N, you could have like a huge set of functions, but you know that effectively on these endpoints you have at most SFN different behaviors from your classifiers. So you just have like n different. Actually, you just have like big N different functions. Like you cannot distinguish more behaviors than that.
So right. So that's true.
So yeah, you could have like an infinite set of functions, but you don't. Like if you see endpoints, you don't distinguish more than SFN.
So my question is, which one is following from which in your argument?
BC follows from the finite version.
But what if your function class has infinite elements?
Doesn't matter because you have endpoints and you just see.
Right, but that's the lowercase n. The capital N is the number of functions.
Yeah, but the number of different classifiers you have from F
Right.
F is n.
So you have n points.
Yeah.
The number of different classifiers can be 2 to the n, right?
No,
SFN.
Sure.
infinite.
This what? So n is the number of training size.
Still, the number of classifiers is still infinite.
Capital F could be infinite.
Infinity, but the number of behaviors that these classifier, the number of ways in which this classifier
Can behave on those n.
behave is just SFN.
Right. It's
So you effectively have just SFN different.
right. So that's the intuition, but
But the real risk, so you can't.
In the expectation, there is the true risk, and that can have infinite domain values.
right. So this. I mean, I can see your intuition, but it's not a formal proof. All right, so we know this, and from Sauer lemma, what we can do that we can upper bound this SFN with this expression n plus 1 to the VCF. So the log SFN can be upper bounded with VC times log n plus 1. And I have log 2 because of this too. All right, and originally we're carrying, so our main interest is the estimation error, this expression. And we know that the estimation error can be upper bound with 2 times this supremum. And now we have bound on the expectation of this supremum, which is this expression. So at the end, what we get, that we have a bound on the expectation of this difference. So this expected estimation error can be upper bounded if you put things together 4 times VC log n plus 1 divided by n. So what we can see now, if you have a fixed VC dimension, even if the function class has infinite many elements, but the VC dimension is finite, then the estimation error, if you use empirical risk minimization, is going to 0 with square root of n rate. Any question on this? All right, so this is what we know. And in some special cases, we know the VC dimension. For example, we discussed if you are in a d-dimensional space and you have linear classifiers, then the VC dimension is just d plus 1. We can plug the d plus 1 to the VC dimension here, and then what we have is that the estimation error can be upper bounded this way in d-dimensional spaces. If you do a feature map first to a, I don't know, d prime dimensional space, then of course you just need to replace this d with d prime. So after feature transformation, you will have this error on the estimation error. So d prime is the dimension of your feature space.
What happens then if you use, for example, vector machines with Gaussian?
Yeah, so these theorems don't say anything about those.
They don't apply? We don't know.
So there's theory how to handle support vector machines with Gaussian kernel and to prove that they do something reasonable. But these theorems don't say anything about that.
Is it because d prime becomes plus?
It's because this d prime would be infinite if you use Gaussian kernel. If you use polynomial kernel, that's a different story. Then, of course, this would be a finite number.
So this implies that the feature map actually leads to a higher chance of overfitting?
Sorry, this implies that the feature map
Leads to more overfitting?
So if you go to a higher dimensional space, then you might overfit easily.
So basically this means that it doesn't help you that you're projecting from a lower dimensional space. The bound is still the higher dimensional space, which can hurt you.
So the higher dimensional space can hurt you, right? But so what you do that you can do a nonlinear map that goes from a space, small dimensional space, to a higher dimensional space. And in that higher dimensional space, you can do linear classification. And for that linear classification, we have theory how the estimation error would behave in that dimension. But the cost you pay is here that you will have d prime here, not d. Okay, and again, this is a theorem on the expectation of the risk, true risk of your empirical risk minimizer classifier minus the true risk of the best possible classifier achievable in your function class F. All right. So we bounded this expectation. But originally we cared about not just the expectation of this random variable, but the distribution of this random variable. And we just proved it with McDermid inequality that this supremum is close to the expectation of this. And that's the concentration bound. On this expectation, the VC inequality told us this bound. If you put all these two, the McDermid inequality and the VC inequality together, then you get this VC theorem, which bounds this random variable with the tail inequality. Instead of using bound on the expectation of this random variable, we bound the tail behavior of this random variable. And then again, you can do the same thing, that you can replace this SF, the shuttering coefficients, with bounds on with VC dimension, either using this or this. Okay. In some books you can see this inequality, in some books you can see this inequality. They are almost the same. All right, so another thing you can do, if we have this inequality on the top line, then you can do inversion on this inequality as well, and then you would get something like this, that if delta is small, then with high probability this inequality holds. And again, we just need to bound the log of the shuttering coefficients. And in this case, for example, we can choose this inequality instead of this, doesn't matter too much. And then you would get an inequality looking like this. And at the end, of course, we care about the estimation error, which is less than 2 times the supremum that we just bounded. So if you put everything together, you get that we can get a bound on the tail behavior of the estimation error. So this estimation error, we can prove that with high probability, the estimation error is less than this quantity. In the previous slide, we bounded the expectation of this guy. And now we bound the tail behavior of this guy. Any questions? Again, so what's the message of this? If you have a finite VC dimension, then the estimation error, on the estimation error, you have this square root of n bound. So with high probability, the estimation error is going to 0 with rate square root of n.
Is there a straight log in there or something?
Yeah, so, yeah. So that's not very too much about this log. They are small. So I mean, in n, these are constants except this log n. So it's log n divided by square root of n. All right, so this is what we did. What we care about really is that we want classifiers that achieve the base risk. So you want the risk of your classifier to be close to the base risk as much as possible. What we did that we fixed the function class f, and then we analyzed with what kind of speed this estimation error can go to 0. In practice, what you do actually is not just this, but it's even more complicated. You increase the function class f with n, and sometimes how people do that they choose function classes with increasing VC dimensions. But how to do it right, that can be quite complicated. So any questions about these results? Do they make sense? Okay, so I know that the equations can be quite complicated. So how you can learn about that you go home, you look at the equations, check where you got lost, and you ask me if you have questions on them. So other difficulty is that we didn't prove everything, because then it would take forever. We just proved some main building blocks. But there are many tiny details that we didn't prove. Any questions?
So are they being used for model selection
Exactly, yep.
How would you do that? So do you directly compare the VC dimensions?
So for some function classes, you can calculate the VC dimension, and you choose VC dimension that has the right complexity for you. So for example, that's used for decision trees, And if you want, I can send you papers on it, how using the VC dimension of decision trees is used for choosing the right model complexity. The issue is that we use these bounds to select the right model, but these bounds in practice might be quite loose. But oh well. Okay.
So in practice, usually what's is there a best way of selecting a model? Is cross-validation or something? Do you have enough data or it varies?
So it varies really. In some cases you cannot afford cross-validation.
It's too big.
Yes.
Not even bootstrapping.
Right, it would take forever. Sometimes you do bootstrapping, sometimes you use cross-validation, sometimes you can use this, so there is no general recipe that I would say you should do this. There are these other criteria like AIC, BIC also used. Sometimes they fail completely. Sometimes they are working nicely. And there are theorems, what are those conditions when they work nicely, but in practice, checking those conditions can be again difficult. So
what happens if sometimes you use BIC or AIC and it tells you oh, this model is supposed to have better likelihood or something, and then you compute some tail bounds and then tells you the other models.
Right. So at the end, they
just trust your intuition.
Yes. You just have to try them in practice and see which one works. Because really, you can see cases where someone says, in this case, AIC worked fine for complexity selection, but I can show you papers where they just completely failed, AIC and BIC. All right, so here is the question. Do you want to see the proof of the Sauer's lemma, or do you want to see some results on manifold learning? Let's vote. Manifold learning. Sauer lemma. I'm the only one? All right. So I recommend you to check the proof in the slides because it's very cute. And it's not that trivial how to prove it. All right, so we only have 20 minutes, so I will try to be quick on this, okay? So what we mean on manifold, so I will not be formal at all here. I'm just saying that a manifold is that if you, so manifold is any kind of object that if you look at that object from close enough, it looks flat. Okay, that's the informal definition. So all these kind of guys, they are manifolds. These are one-dimensional manifolds. These are two-dimensional manifolds because if you look at them from close enough, they look like two-dimensional flat surfaces. Would be preserved.
All pairwise distances.
All pairwise distances. Or even if not preserved, then I can ask what's right. What's the best embedding that would keep most of these distances? All right, so here is what we are going to do. So say originally we had a data set and in this data set we have feature vectors xi, xj, xk. And the distances between these feature vectors are denoted with d. So dkj is the distance between xi, xj, dij is the distance between xi, xj, and so on. Then using the cosine law, I know that this equation holds. Oops. Where cosine alpha is this the cosine of this angle. So that's the cosine law. let the inner product between these two vectors be denoted with Bij. So we know that Bij is the product of these distances times the cosine alpha. And from these two equations, we can see that the inner product between these two vectors, so the inner product between xi minus xk and xj minus xk, I can get this inner product using these distances. So if you give me distances only between feature vectors, I can use those distances to estimate this kind of inner product between these vectors. All right. If your data is centered, we assume the data is centered, then using similar arguments that I just did in the previous slide, using distances, Dij, Di, and Dil, and so on. So using all kind of distances between feature vectors, you can calculate the inner products between any two feature vectors. Okay, so you can prove that this equation holds if the inner product between xi and xj can be calculated using this equation. And what we are going to do in multidimensional scaling, you got the distances between any of those 2 points, xi and xj. You calculate the inner product between xi and xj using these distances. And you want to find y1, y2, yn points in a low-dimensional space such that you want to keep all these inner products. So that's one version of multidimensional scaling, but there are lots of other versions. And here is an algorithm that can do this. So you calculate these inner products. In other words, you calculate this gram matrix. In this gram matrix, you calculate the top k eigenvectors. These are psi1, psi2, psi_k. And then we right. So this you are in an n-dimensional space. So you had n feature vectors. So G, this gram matrix, is n by n. You calculate the top k eigenvectors of G. So you calculate the top k n-dimensional vectors. So these are psi1, psi2, psi_k. So this is an n times k matrix. Lambda are the top k eigenvalues of this matrix G. And then we just say that let the embedded points be y1, y2, yn be defined with this matrix product. Okay, so you just need to use the eigenvectors and eigenvalues of this matrix. You know, it's very similar to PCA. So when we discuss PCA, then we notice that PCA works on a X times X transpose matrix, and MDS, now it just works on a X transpose X matrix, but we do the same kind of things. We want to find the eigenvectors of this matrix. And if you do this embedding, so is it clear what we do? It shouldn't be clear why exactly we do that, but the algorithm should be clear. So from the distances, you calculate these inner products. From this inner product matrix, you calculate the eigenvectors and eigenvalues. Using those eigenvectors, eigenvalues, you generate these points, and you are done. So then here is an application of this. So these are cities in the USA, and you can see the distances between these cities. So that's the input of your algorithm. And the question is if you can reconstruct where these cities are in the US or in 2D. And this is a result if you run that MDS algorithm that we just proved, that I just showed. So it's not too bad, right? You might need to flip things up. But it's not too bad other than that. So here is another data set that I tried. So again, you can see cities in the US, and here is the result of a multidimensional scaling embedding using that data. It's not too bad, right? So at least it kept some structure. Okay, so this is MDS. So I want to show some couple of other algorithms. So this algorithm is called isomap. It means isometric feature mapping. So what you do is that you have a data matrix, x1, x2, xn, and between any 2 points, you try to calculate or at least estimate the geodesic distance between these points. So what does it mean?
Geodesic respect to what?
Right. So with respect to the manifold that they might be. Of course, we don't know that manifold. That's the issue. But what you do is that you at least you can approximate. So this is what you do in practice. Say this is your data set. You want to calculate the geodesic distance from this point to this point. So what you do that you fit, say, a k nearest neighbor graph to this data set. So in each point, you just select the k nearest neighbors or the epsilon nearest neighbors. And then you try to get from this point to this point using the edges of this nearest neighbor graph. Okay? So here is one point, here is the second point, and using these edges of the nearest neighbor graph, you want to get to this point, and you want to find the shortest distance using this nearest neighbor graph. So this is how you approximate the geodesic distance, just using k nearest neighbor graphs or epsilon nearest neighbor graphs. And you do that between any 2 points in your data set. And then you use multidimensional scaling. Okay? So you estimate, instead of using the Euclidean distance between these points in the data set, you estimate the geodesic distance between these points. So again, geodesic distance that you are allowed to move only to nearest neighbors from each point. So from this point, you are allowed to move to its nearest neighbors. Say you moved here. Then from this point, you are allowed to move its nearest neighbors. Say you moved here. And you want to find that path to this point that has minimum lengths, and you can just move to nearest neighbors, local neighbors.
Doesn't that mean you have to do like graph search over the entire data set then?
You can, yes, so you can.
Like is that computationally?
It's computationally expensive, but oh well. Even MDS, that's computationally expensive.
Well, nearest neighbor, so you have a set of nearest neighbors, or you have set the fixed
In each
distance?
point.
Because
So, okay.
there's only one nearest neighbor usually.
Okay, so each point, you can say each point, around each point, you can select the case, say 5 nearest neighbors. Okay, or 10 nearest neighbors, or epsilon nearest neighbors, which means what are those points that are in an epsilon ball around point. You do that for each point, and then you are allowed to move from each point to its neighbors. So from this point, I move to my neighbor. From this point, I move to my neighbor. And you want to calculate what's the shortest path on this graph between any 2 points, and what's the distances. You use this distance matrix as an input for the multidimensional scaling algorithm, and that's your isomap algorithm. So it's very simple, right? And still it was published, I don't know, it was published in Nature or Science. So sometimes you don't need much for a publication in these journals.
When was it published? When was
When,
You had 2000.
early 2000s, yeah. They are not that old, these algorithms. Okay, so here is a result on images. So images are high-dimensional vectors, and for each image, you calculate what are the nearest neighbor images using Euclidean distance. Using these distances, you estimate the geodesic distance between any 2 images. And then you use multidimensional scaling to embed these images, say, to 2D. And as you can see, it keeps some structure that this image turns left, these images are turning left, and top. And these images to right and top, right and bottom, and so on. So this way you can show the nonlinear structure in your data set. You can do the same thing with images of digits, and this is one result. Okay, you can do this for interpolation as well. That, for example, you select 2 points in your data set, and then using this graph, k-nearest neighbor graph or epsilon graph, you want to go from this point to this point, and you can show those images that you go through. And then ideally you will see some smooth transition from one image to another image. Yes?
Are there any theoretical guarantees of this that would help us choose the number of neighbors?
Not really. So not on these kind of algorithms.
Can you have islands, or do you have to do something to make sure it's connected?
So I think isomap. So I have a table on that. So let me show that a bit later. So that's a good question. That what kind of properties of these manifolds has to be? That can they have islands? Can they have holes in it, corners, and so on?
So an island, just a disconnected graph.
So I guess you mean that they are just far from. Yeah. So these are some results if you do on this isomap interpolation on images of a hand opening and closing. So the nice thing that if you just use standard Euclidean distances between images, that wouldn't work at all. Because the distances, Euclidean distances between these row images, they are just big, no matter what images you choose. All right, so another algorithm I want to show very quickly because that's famous.
If the distances are big, so how do you do nearest neighbor?
So except your nearest neighbors, but the other distances, they are very big. Okay. So in local linear embedding, you have, say, m data points in capital D dimension. And what you do that you try to reconstruct, first you select some nearest neighbors for xi. So for example, I selected these 5 nearest neighbors. And then I want to reconstruct this xi point using its neighbors. So what do I mean on that? That I want to solve this problem. What's that W matrix that minimizes this expression? So xi has to be reconstructed using its neighbors. So wij are some weights if j is a neighbor of xi and 0 otherwise. Does it make sense? So each point xi, you want to reconstruct from its nearest neighbors. And on reconstruct, I mean you want to minimize this. You calculate these w's. And in the next step, using these w weights, you want to reconstruct the original points or embedded points. So let z points be in a lower dimensional space, z1, z2, zm. Say in a lower dimensional m. Now we know w's, and you want to minimize this expression in Z. Okay, so first you try to find those weights for your given. So you have a data set, you try to find those weights that minimize these reconstructions. Then you have these weights, and you replace these x's with lower dimensional vectors, say z's, keeping the same weights.
Seems really similar to like autoencoder learning.
So it's similar in that sense that you have these w's and you use them. So you can do non-linear, sure. And you need to have some other constraints. For example, you might assume that the points are centered, and for w's you also assume that they sum to 1. So yes. And I just want to show some results. So if this is your original data set, and you choose the number of neighbors in the right way, and then you embed this data set into 2D, then it would unfold this data set. Here we embedded the digits, the images of these digits into 1D. And these are the embedded images. In this data set, you have these shifted faces. And if you embed these images into 2D, then you would get this embedding where, say, this would correspond to this corner, this would correspond to this corner, this would be in the center, and so on. And in the slides, you can see some other examples. So I have to stop here. I just want to mention that there are some other slides on other manifold learning algorithms, such as maximum variance unfolding, and some results on that. There are slides on Laplacian eigenmap manifold learning algorithms. There are some results on variational mixture of factor analyzers. And there's a MATLAB package called Many, where you can try, I think, like 8 different manifold learning algorithms on different data sets. And this is where you can compare algorithms and answer your question, what if there's a hole in my data set? Then which algorithm would work, which wouldn't work? And that is this table that I just mentioned, that some algorithms like multidimensional scaling PCA, isomap, LLE, Hessian eigenmaps, Laplacian eigenmaps, diffusion map, k-nearest neighbor diffusion map. So they are all manifold learning algorithms. And this is a table how well they work if there are clusters in your data set, or islands, or if there are corners in the data set and so on. So you can look at this table, and you can look at some other results. For example, what the diffusion map would do on this kind of data set if you embed this data set to 2D with different parameters. Or if you have this kind of cluster data set and you would embed that.
What's LE?
Local linear embedding. Right. So how this algorithm would work on high-dimensional data set. So this data set was this blob here that was moving around. That was the image. And we tried to embed that into 2D. And these are some of the results that we got. So for example, the LLE that just crashed on this data set. You can see some other interesting data sets. So these are 3-dimensional data sets, and these are the results with multidimensional scaling, PCA, isomap, LLE, Hessian LLE, and so on. These are, again, interesting data sets. So what happens if your data has corners, like this, which algorithm would work, which wouldn't work? You can see that multidimensional scaling, it failed in this case. PCA failed as well. And this is what happens if you have holes. So here we have a hole in the data set, and then these are the results. In this case, this Hessian local linear embedding that worked very well, but some of the others failed miserably. All right. So there are lots of details in the slides, so please look at them. If you have questions, then just contact me. Similarly, with learning theory, some of the parts were pretty quick, and how you can understand really, you go home, look at the slides, look at the related literature. I gave some pointers on the class website. You can look at them too, and ask me if you have any questions. All right? So see you next week.
Masz. Ja to question over minimax. So how does the VC bound look like for the minimax?
So what happens with VC? Do you have those papers?
I don't know.
So in the theory that we discussed, we assume that there's a PXY distribution, right? In minimax, the situation is even more complicated because you assume that you have a function of probability distribution. Okay, so we assumed in the theory we discussed here that there's a probability distribution PXY, and there's a family of classifiers F. And you wanted to find the best classifier that classifies